So welcome to our review for the physics unit in grade 9 science about electricity. We're going to talk about static electricity right now, and you'll notice that afterwards we'll talk about circuits to make sure that you're ready for the knowledge for the exam coming up at the end of this semester. So let's see if we can look at what is happening with static electricity to start with. So if I go here, there you go. So this is a PhET simulation. Hopefully you had a chance to do this in class. If it happens that you have a balloon like this, and the balloon, if you notice, we have a positive and a negative charge, positive, negative. So this means that the balloon is neutral. We have here a sweater. If you notice, there's the same number of positive charges than negative charges. And on the wall right here, you have the same number of positive charges than negative charges. So what happens here when you have static electricity is that charges can move from one material to another when you are dealing with insulator. So an insulator is a material that once you have a charge in one place, it has nowhere to move. So some of you may have played at home. So when you have here a balloon, you rub on your hair and you can put it on the wall and it will stay on the wall. So here you have a balloon. The balloon is attracting the electrons from our hair, and now I have a charged object. Why is it charged? Because the electrons on the surface have nowhere to go. So let's see. So if I go back to my simulation, very nice. So we have the balloon here. We can charge an object by friction. So if I go and I rub the balloon on the sweater, like I mentioned earlier, rub the balloon on our hair, charges will move around like this. So here by friction, you notice that the balloon has attracted the electrons and the sweater somehow lost its electrons. What happens here is that some materials attract strongly electrons, and the sweater here made of wool had electrons, attracts electrons, but much more weakly. So that means that when there is friction, what will happen? The electrons are going to the balloon. So if I let the balloon go, so here my mouse is clicking on the balloon. If I let it go, I notice that the negative charge of the balloon is attracted to the positive charge of the sweater. So this is what we had friction and we had transfer of electrons. So here, that's the first thing, perfect. The next one is what I call charging by induction. So if I have my negative balloon here and I bring it closer to the wall, notice what happens to the electrons. You notice that the electrons are moving away from the edge of the wall. And I call it charging by induction because the negative charge of the balloon is pushing the electrons further away from the surface of the wall. So what will happen? So if I let it go, the balloon will stay stuck on the wall. The wall is still neutral, but the induction here of the negative charges makes it that there's a little bit of positive right here. So if I move it down here, you'll notice that the influence of the negative balloon changes. Now, over time, the balloon will not stay on the wall forever. What will happen? The electrons here will jump into some like water droplets in the air. You've got dust and particles and different compounds. Or the electrons will be attracted to the positive charge right here and will jump on the wall. So what will happen? The wall will become more and more negative. The balloon here will lose its charges. So what will happen? We have the gravity that will take over and the balloon will go down. So that's something to keep in mind. Perfect. Now, if you look at the particularities of charges, in static electricity, we have objects that are insulator that have charges. So what's interesting? When you have the charges that are the same, they repel each other. Now, what's interesting, when the charges are different, they will attract each other. So if you have a positive charge and negative charge, they will attract. If you have a negative and a positive charge, they will attract. But also if you have either positive or negative, they will be attracted to a neutral object because the charges are different. And that's interesting because we can use this and use examples in the industries where if you have an electrostatic filter, that means that you have pollutant going through static charged filters. They will have particles attracted to positive and negative and even neutral particles. And what will happen? It will clear up the air. If you have, for example, paint, you're spraying paint, you can give a charge to the paint droplet that will increase the adhesion of the paint on the metal surface, and therefore the paint job will be much better. So these are examples when we are thinking of static electricity. So let's see how my review is going. The next topic we're going to look into will be about electroscopes. So let's see if I can do a few drawings for you, and I'll be back in a moment. When we think of static electricity, one piece of equipment we use are electroscopes. One piece of equipment is electroscope. Very good. So let's see if we can go from there. So an electroscope is a piece of equipment that is, here we have a metallic ball. We have a stem and two little leaves of metals or metallic compounds. So what happens here is that the electrons can move freely. When we talked about static electricity, so far we talked about insulators. Now, keeping in mind that we can give a charge to different matter, because over the history, scientists notice that when you are creating, you have friction, energy is given to electrons. So let's have a look. If you rub your hands like this, you notice it gets warm a little bit. That the friction is creating energy. And that energy gives enough energy for electrons to move from one matter to another. So if I take the balloon here and I rub on my hair, the friction will take electrons from my hair and they will jump on the balloon right here. So here is an example of, this is a hard rubber. It's made of ebonite. If I take here, I have some rabbit's fur and I have some friction. What will happen here is that I end up with, so I don't know if you can see, oops, if you can see how the hair are being attracted to this stick right here, because the electrons went to this ebonite stick, and at the same time, the hair lost their electrons, and now they're more positive. So if you can see, the pieces of hair here are all over the place. Now if I bring this again, you can see how they are attracted. Perfect. How do we know what's happening here? We have what we call the triboelectric series. So let's see if I can show that to you. There you go. Oops. Let's see if I can move it this way. Perfect. The triboelectric series goes like this. It shows that we have materials that have low electron affinities. That means that they are holding on their electrons weakly. Whereas we have high electron affinity, which means that they are attracting electrons strongly. So if you are to create friction between matter at the upper part of the triboelectric series, there you go. We have here human hair, or you have, for example, rabbit fur. If you have friction, electrons will be easily moving away. So here we have human hair. My hair would become more positive. We have cat fur here, or we also have what we call rabbit's fur. At the other end, we have rubber, we have polyester and PVC. What's interesting with those is that they are attracting strongly the electrons. So that means that the electrons from these materials that are insulator will be moved down the list here. So you have rubber, like my balloon, that will be more negative. So that's one way to know what materials are positive or negative. And this list has been built over the decades and 150 years with scientists playing with that list. So let's see. Let's go back to our electroscope. If I have here my ebonite stick that is now negative, so what did I do? We have a stick like this and rabbit's fur. We have here a neutral electroscope. We know it's neutral because if you look, same number of positive and negative charges. So here everything works well. Now what happens though is that when you bring the stick closer to the electroscope without touching it, we have what we call induction. The induction is that the negative charges here on the stick will influence the electrons on the electroscope, and the electrons will be moving further away from the stick. So here you have the electrons that will be moving down, and now you have more electrons at the bottom, and therefore you have the two little leaves that will be moving from each other. And if you go on my channel, I have an example of how this works. I had a video with an electroscope that I had that I've used in the past. Perfect. So here it's by induction. There's nothing is touching. Earlier, when I used here my ebonite stick with my piece of fur, we have here charging by contact. I charge by contact because by friction, I was able to move electrons to this object. So here, this is what I've got so far. Now, what happens though is that if there is contact, so earlier I was able to create a charge by contact and friction. If I go here and I have let's see, let's change side. If I go to this electroscope, I have here my stick that is not touching. What happens is because I have a positive ball right here, the positive charge is attracting the electrons from the stick. So that means that electrons will be moving in the electroscope. So that means that 1, 2, 3. So 1, 2. Let's say 1, 2, 3, 4. So let's see, like this. 1, 2, 3, 4. So earlier I had 2 extra electrons at the end of each of these leaves. They separated. Now here, because I touch the ball here by contact, electrons are jumping in. So now I have 4 electrons that are adding to the whole charge of the electroscope. This is what we call charging by contact. Perfect. Now what's interesting is that if I move away my negatively charged stick, what I notice is that now it's less negative because more electrons are here, and now the electrons will be distributing themselves evenly in the electroscope. So here I have a situation where I was able to charge by induction. Charged by induction. We have here an object that was charged using another material that was charged. So here I had a negatively charged object that can negatively charge the electroscope. Now this would work the same if you had a positively charged object. If you had a positively charged object, what would happen here? The positive would attract the electrons to the top here, therefore putting the 2 little leaves positive, therefore they will be separating. And by touching here, the electrons will be jumping on the stick because the stick is positive, attracting electrons. And then when you would take away the object that was positive, you would create a positively charged object that was charged by induction. So both works well, both for positive and negative object. So this is the work we did on induction. So the last example we're going to talk about today will be how does lightning form? Lightning form from this idea of charging by friction, having induction, and having what we called grounding. So I'm going to take a moment to do some drawing, and then we'll be able to follow. So give me a moment. Now let's see if we can talk about how lightning is being produced and what does it mean when we talk about grounding. So let's see what we've got. So first of all, if I have a cloud here in the environment, in the cloud, at the beginning you have a neutral object, and let's see if I can. So here I have a neutral cloud that has the same number of positive and negative charges, and here I have a tree, same number of positive and negative charges. Same thing with the human, same number of positive charges and negative charges, and the ground is gray. Now what's happening is that when you have clouds, so if you have, for example, a cold front and a warmer air in the atmosphere, what would happen is that the warmer air would have more water droplets, and water is a great way to absorb electrons. So when you have a cold air that tends to be drier, when there's a friction between the two types of air, there's a friction. So here you can charge a cloud by friction. So what will happen is that you have the dry air that will lose electrons, and you would have water in the clouds accumulating electrons. So if you have a cloud that has more and more electrons, what happens is that these electrons don't want to be close to each other, and on top of that, they're creating by induction the movement of electrons in the environment. So that means here that on this tree that had electrons at the top, the electrons will be going towards the roots. And here you have the electrons that are close to the surface that are moving a bit further down here in the ground. And this happens because you have sap in the trees and you have water with electrolytes, and therefore electrons can move freely. But that happens the same way of a human. If you have a human and you have induction because there's electrons that are right here, electrons will be pushed away. You end up with a tree here that is now positive and a human that is now also have a positive head. So what will happen slowly? The electrons that can jump from one droplet to the other and going in piece of dust in the atmosphere. Eventually, you have lightning that will touch here the tree. And you've seen photos, you've seen videos of lightning striking trees because there's a difference between the charge of the tree and the cloud, and that is done by induction. But in the same way, if you have a human right here with a positive charge on its head, it's like welcoming the possibility of having lightning touching that person. And that's why if you are in the summer playing soccer, playing golf, going for a walk, or you are swimming on the lake and you can hear thunder, which means that lightning is present, it's very important to move from a flat area. So usually rain is coming, people don't like it as much, people go inside a building and people are safe. It's important because if you're on a flat surface, so here if I have a cut tree, for example, what happens? You end up with only one human with a positive charge, and that's the closest object to the negatively charged cloud, and that's why we have lightning. Like this. So this happens with nature. What happens when you have a large tower? So there's large towers in most cities, high building, skyscrapers. Like this, you can have houses as well with little chimney. What happens is that you end up, when you have a cloud that is negative, it's looking for a place to be able to move away. The tip of our tower becomes positive, tip of building, the tip of the chimneys of houses. And therefore, these are great ways for electrons to be able to escape. The only way we can protect towers like this, because if you have a big influx of electrons, you have this, and there's like it could be the tens of thousands of volts and so many electrons that cannot handle insulator, you'd have a tower that would explode. You'd have a chimney on a house that would explode. So what we have cable that are installed in towers and in buildings that brings the wire from the tip here of the highest point to the ground, the tip of the highest point to the ground. And some people, their job is to make sure this happens. This is what we call grounding. And and what's the name of it? So we have grounding due to, we call them lightning rods. What are lightning rods? They're rods at the top of higher places that are linked with a wire to the ground to protect the different structure. Now, the reason why that happens, we have a cloud full of electrons isolated in the atmosphere, charged by friction and through induction, creating charges in buildings. And they are discharged. They are discharged in order to ground themselves, in order to what we call neutralize themselves. And that's part of the link between static electricity and what's happening in the real world. When we are discussing circuits, we have to see how we can easily draw them. So here on the board, you can see how we can do that. We have a series of symbols we can use, and these are used in Canada and many of those in the United States. I know sometimes, depending where you are, different continents, different countries have different ways of tracing them. But here we have conductors. They're full line with here, if you have intersections, you have a dot. You have here the switches. This is an open switch. No electrons can go through. A closed switch where electrons can go through. Therefore, if you have a motor or a light, it's on. You have here an energy cell. So here we have a small vertical line and a long one. And then if you have many energy cells that create a battery, then we have these symbols here. So usually we don't go more than 3 times what they are, and then we put a number to say how many they are. So you could put 6 volts here. You could put 12 volts as well. You have here an A in a circle, which is an ammeter. It's a tool to measure how many electrons are moving in one place, a specific place in your circuit at a specific time. You have the voltmeter, which is measuring the energy of the electrons going through. You have here an X in a circle. Sometimes you have a little wiggle in a circle. These are what we call bulbs. It's a way for energy to transfer, there you go, the energy of the electrons that was gathered in the battery and transform into light. And if you have an M like this one, this is a motor. Keeping in mind that when you have energy coming from a source, for example, a battery, the energy of the electrons often can be simplified in 4 basic type of energy. One is light. So it goes from the energy into light energy or sound energy. It could also be movement or heat. If you want to have a good example, if you think of a phone is a great tool that covers all of them. Because we have, if you look at your screen for a smartphone, you have light. You also have, if you have a phone call, you have a speaker. So when you listen to music, for example, you also have heat. So your phone can heat up, especially if we use a flashlight or specific, or if you charge your phone. And the third one is movement. Some people have a vibrating movement, and therefore a phone is a great way to look at that. Excellent. So these are all the symbols for that. Now, the 2 different types of circuits are what we call the series circuit and the parallel circuit. What's interesting with the series circuit is that there's only one way for electrons to go through. So if you look here, this is negative and positive. We have the electrons that are moving this way from the negative side towards the positive side, like this. All the electrons are getting their energy here, are going through the switch. This one is closed, therefore the electrons can go through. and drop all of the energy in the bulb here. So here you would have 1.5 volt of energy being dropped here before the electrons go back to the source to get more energy. Here I have what I call a parallel circuit. What's interesting with this one is that when we have the electrons that are going through the circuit, the electrons here going through the switch, it's closed so the electrons can go, but here the electrons can go in 3 different paths. So if you think of, if you're driving in a car or on a bicycle, you can have one trail, but there's only one place for the bike to go through. But here, if you have 3 different trails, you have 3 different paths for the bikes to go through. So here you can, if you have only one trail, you have one, let's say the lineup of bikes will be one after the other. For this one here, you have 3 different paths. That means you can have 3 times as many bikes that could go in this example here. So this is the difference between series and parallel circuit. Now, some people say, well, they look complicated. Keep in mind that you can always simplify a circuit by hiding a portion. So if you think of this one, this looks like a parallel circuit. But if I hide here the last 2, this looks like a simple a series circuit. If I hide these 2 here, this is like a series circuit. So my trick when you are doing calculations or you're working with parallel circuits or complex circuits, you can hide different portions so that you can easily figure out what is going on in the circuit. So that is the first bit here. The next thing to look into would be how do we know how the energy is going through the circuit? So let's see if we can look at the basics of a circuit, and then we're going to bring in about maybe 3 minutes the Ohm's law, which is allowing us to do calculations with the data of our circuit. So let's see if I can trace the circuit for us. So let's see at some particular situation when we have a circuit, so we have a better feel of what the Ohm's law will be in a moment. When you have a circuit like this, as I mentioned, we have here a source with 6 volt, and we have here, so if I hide the second part, this would look like a series circuit. If I hide this one, it would be like a series circuit. So let's see what we've got. First of all, if you are having a circuit, we know that we have electrons that are moving. They are moving because the switch is closed here. You're going to say, why is it moving this way? If you have a negative end of your source and a positive end, as soon as you close your switch, what will happen is that, first of all, the positive end here will attract electrons. By attracting electrons, it will attract electrons here. So that means it will bring electrons towards this end. Now, keeping in mind that the other end, which is negative, the electrons are repelling each other. So electrons will be moving away. So that as soon as you close the circuit, electrons will be moving away. Now, if you have here 6 volts, so this is the tension. So if you have the tension in a circuit, the tension is the energy of the electrons. The current is the number of electrons going through the circuit at one place per second. So I want to know at this spot here, how many electrons are going through. At this spot right here, let's see if I can put my marker, at this spot right here, or at this spot right here. Now, these are 2 pieces of information that are useful. So let's start at the source right here. So if I have electrons moving this way, what will happen? They will go to the first ball here. So that means that electrons have energy, will go up, go through the bulb, and go back to the source. So that means that the bulb here will use 6 volt of energy. Why would it use 6 volt? Think of you and food. You leave home in the morning with the breakfast, you go and do an activity in the morning, you go back home, you get lunch, and then you do an activity in the afternoon, you go back to home to get some dinner. Interestingly enough, for a person that has always the same weight, it will get food energy, use food energy, and come back here to get more food energy. So in a perfect circle, then the person will say the same way because it absorbed the same energy that it's giving. And that's why we have here 6 volts for this bulb. So that means that all the electrons going down here have 6 volts. So that means that all the electrons going here will also have 6 volts. However, here we have 2 bulbs. Keeping in mind that all the bulbs in this example are exactly the same, when you have 6 volts of energy for the electrons, it has to give energy here, and then it has to give energy here before it comes back. So that means that each of the electrons will give 3 volts of energy at each of the bulbs here. So if you were to think, for example, if you are a student or you're someone who goes to work, we have here energy. We get some food energy. We go here. However, you have 2 activities to do in the morning, so that you cannot give 100% of all your energy here because you'll be exhausted for the second part before you go and get more energy. So what will happen? Electrons are going through. Notice there's some work to do here, and then some work that goes here. So within a fraction of a second, it will even out how much energy is given to each of the bulbs here. So that's how we know that half the energy of the electrons are going here. Perfect. Now, how do we measure this energy? We use what we call a voltmeter. So the voltmeter is right here. We are connecting a voltmeter in parallel. So here, like this, and like this. And the reason why we measure the voltage or the tension with a parallel connection is that we want to know how much energy, what is the difference in energy before it goes through the battery and after it goes out of the battery. That gives us how many volts, how much energy is gathered in the battery. When it goes through a bulb like this, we want to know in a parallel connection, what is the difference between the energy of the electrons before it goes through the bulb and after it gets through the bulb. So it will tell us how much energy is given here, and then it will go this way. If you have 2 bulbs, energy is going here at 6 volts. We go here, 3 will be given there, 3 will be given there. So for a total of 6, and everything is going back here. We also have what we call the ammeter. The ammeter is there to measure how many electrons. So that means that in order to find the answer, we have to break our circuits and we have to add the ammeters. So let's see if I can add a few here. Perfect. So here we have cut the circuits. So it's like a water pipe. You're cutting the water pipe and you want to know how much water is going through this place. So you have to cut it and you have to look and see how much water comes out. I'll get my marker. Give me a second. Good. So how do we look at numbers here? So here I'm going to say that there is one amp going through this circuit right here. And what I will say is that I have 1.5 amp going through this ammeter right here. So here we have the total number of electrons going through this way. We have 1 amp going here before it goes back to the source. So that means that if 1 amp is going down here, that means that in the part here, I would have 0.5 amp left. So these are numbers we can calculate. Now, there's a scientist called Ohms, and he was looking at those circuits, and at some point he was trying to look, is there a correlation between the tension and the current? And he came across his law that we call the Ohm's law. So let's see if I can write it down for us. So let's look at some calculations here. So Ohm's law is the following. There's a relationship between the tension, which is in volt, and it is the current times the resistance. Now, the resistance, what it is that it's the properties of matter that are there to slow down the electrons so that there's a transfer of energy. So here, the electrons will be slowed down so that the energy of the electrons in the circuit will be transferred into light. If you have a motor, it will transfer the energy of the electrons into rotation, which is what we have with motor. If it's a heater, it will transform the energy of the electrons in the circuit into heat. Now, what's interesting here, so we have here the tension with the units V in volt times the current with the units of amp, and we have the resistance. And here we have the symbol, which is the omega, that represents ohms. So if you were to look at this calculation, so V equals R times I, if I want to know the resistance of this bulb right here, it is the tension over the current, 6 volt over 1 amp, it gives us 6 ohm. So we have here 6 ohm, which is the characteristic or the resistance of this light bulb right here. So this information could be useful because if you look at the second branch here, I want to know how much current goes through this bulb right here. What you have the same calculations, V equals R times I. So I want to find the current. We have the tension over the resistance, which was calculated. 3 volt over 6 ohms gives us a current of 0.5 amp. So that means that in this branch right here, the current here is 0.5 amps. So the reason why these bulbs here, because they're two, will be not as bright as this one bulb right here, is that in this bulb, you have 6 volts, the energy of the electrons, and there's 1 amp of them. So there's a lot of electrons. For this one here, the reason why it's 3 volts here is that because of the resistance, we have twice as much resistance. That means that the number of electrons will be, will be half as much. And at the same time, it will allow the electrons to give half the voltage here and half the voltage here. And all of this in line with the Ohm's law. And that's interesting because that allows us to get everything together. Then again, if you have a complex circuit, and I know that I've given a lot of examples in class, and I've also done a video a few weeks ago about circuits. Keep in mind that if it looks complex, you can always hide a portion of it to simplify the information you've got, or you can hide a portion here to simplify what you have. Because when things are complicated, you always want to try to break it down in smaller, simpler steps so you can find the answer.